Alrighty, good morning. I'm Jeremiah Jordan.
I'm Rocky Peck.
And our project is design a photovoltaic system for directional signage. Our sponsor for this project is Persona Inc. They're a signage manufacturer based out of Watertown, South Dakota. They serve many big name brands. And for this project, what we're focusing on is directional signage, which lets you use the edge of businesses, and they're backlit. They'll usually have the words enter or exit on them, a little arrow telling where to go, or if you're carrying that coming to that business. So that's what we're focusing on with this project, or just those little signs.
So the current system for Persona's directional signage is that they are all tied to grid power. They have no option for a solar power system. So this comes with two things. One is that they must pay and rely on grid power at all times. And two, that they must trench electrical conduit from the building to the sign, which requires permitting and electrical contractors, which can get very expensive very fast. So our goal is to eliminate this cost and design an off-grid photovoltaic system for Persona's directional signage.
Usually the significance in a solar power conversion project is the energy savings. And while we can save up to $73 a year with the system, our big claim to fame here is actually the reduction in install costs. Most installs, you're going to see around $2,000 to $3,000 savings. And if you're in a really nasty situation where you need underground boring, get around an obstacle, you could save upwards of $7,000. The other thing here too is we save some of the customers a lot of time. There's not as much time associated with the different permits you need. Also, time on hiring different contractors in order to get all the electrical conduit installed and wired up. When Persona first pitched this project to us, they wanted to light 80 GE-LT series LED modules for 12 hours overnight. We knew we needed enough battery capacity to do that. And then for solar side, we knew we needed enough solar generation in order to keep that battery charged from day to day, so that way the system would always be running. But here, Persona threw us a curveball. For aesthetics, they didn't want the panel to exceed 2 foot by 4 foot in size. And the last request they had was that all components in the sign be 12.
So some additional modeling complications, even with the initial constraints that we should account for when doing our modeling. The first one is cloudy conditions. When our solar panels running on a very cloudy day, this can reduce our efficiency down to below 25%. So if we don't account for that, our system is going to fail. Temperature is another thing that we need to keep in mind. As we all know, cold temperatures can decrease battery functionality really fast. And so if we don't account for that, our system is going to fail. Another thing to keep in mind is depth of discharge for our lithium iron phosphate battery. As recommended by our manufacturers that we don't exceed a maximum depth of discharge of 70%, and this will preserve our battery life. Another thing we need to keep in mind are the efficiency losses that we'll face charging and discharging our batteries. There are going to be losses with all that current flow in and out of the battery, so we need to keep that in mind. Panel angle for any solar panel system, solar power system, there is going to be an optimal angle to have your solar panel at. And this is going to depend on your latitude and your time of year. And finally, location. Two things come with location. One is your solar intensity. So being on the equator, you're going to have higher solar intensity versus being up here in Brookings. And another thing that will vary is your day length. Here's a simple system block diagram of our photovoltaic system. So first we have the sun. And the photons from the sun come down and hit our solar panel, which will dislodge the electrons and create our current flow. Then that will go on to the MPPT charge controller, and this item regulates where all the power goes. It regulates what goes in and out of the battery, how much power goes into our LED modules.
So the initial calculations that we did for the project were basically just focused on trying to figure out the relationship between components. We were specifically interested in figuring out how does the number of LED modules give us a load current, how does the load current combined with the number of daylight hours give us the required battery capacity, and then how does the low current combined with the economic charge time. Give us the panel lots, but you can see those calculations. But the main variables that we found out through these initial calculations, so the number of LED models as well as the number of hours they connect. Once we figured out those calculations, we were able to construct what we call a battery model. This basically gives us our minimum component sizes based on the assumption that the system will perform at 100% of the time on a given day. It starts to account for different things that we mentioned earlier, like the battery's performance, the maximum depth discharge, as well as the big level efficiencies. And this is just a sample that we did for August 21st bookings in order to run the being like August 21st. We need a 132 watt panel, a 52 watt battery. Once we had that established, we snowballed that into a new model, which is the annual performance model. So the previous model gives us component sizes based on our desired performance. This model goes the opposite direction. It gives us the system based on the input component sizes. And notably, it starts to account for the performance of the system for the entire year, not just the system day. Some of the important results that we got out of this so that you can get the best bang for your buck at about 0.5 amp hours battery capacity. So if you design this around that size, you'll be in a good spot. We also found out early on that the 2x4 foot screen made it very difficult for us to power and beam outside. You could, however, reduce the LED model down to 40 and get a system for the active screen. And if we do that, we need a 2 watt panel system for that instead. So then, once we had some of those things set up, we went into the time configuration model, which is a solar model. This takes everything that we did earlier on and adds a couple of new things. Specifically, we want to account for the panel's annual tilt, as well as the performance on cloudy days. And this all ultimately benefits monthly the differences in power consumption that the system might go through as you start to talk about a little bit later. So once we had that model, we were able to create the initial system design, which is our home base. This sign assumes that you want to light 40 mods all night in bookings throughout the year. In order to do that, you need a 225 watt panel and a 60 amp hour battery. And you want to go ahead and mount that panel at about 68 degrees so that it maximizes production in 22 months, which is when you need it most around here.
Once we had nailed down most of the modeling at the end of the spring semester, had a general idea what size components we were going to need, and so we started the process of selecting our components for making a prototype. The heart of any solar system is the charge controller, and it's where everything connects and is controlled all of it. So for this, we chose the Victron MT7510. The main reason here is their programmable load control based on panel voltage. You can detect the daytime and nighttime, and it can turn the load on or off based on lowers the LEDs. The other big plus for this is its compatibility with lithium iron phosphate batteries. Not all controllers support them, and they charge differently than lead acid batteries. We also needed specifications for panel short circuit current and open circuit voltage that exceeded our needs. And then with that, for the solar panel, we wanted to get something close to that 2x4 foot, but also maximize the amount of water you can get there. So we went with the Rich Solar M200. It exceeded our minimum panel wattage that we calculated at that time in the spring. And also the panel voltage is higher than battery voltage at all times. Because our charge controller does not have any sort of boost converter in it to pull up a low panel voltage. And not important for our projecting purposes, but if someone wanted to go ahead and use that panel out in the wild, it is also rated for high wind, hail, and cold conditions. Lastly, our battery, we went with the lifetime lithium iron phosphate 50 amp hour. It has an onboard BMS with all sorts of burst polarity, overcurrent, and cold weather detections. And being lithium iron phosphate, it also has very high energy density and pretty lightweight compared to lead acid. And lithium iron phosphate is also fairly stable with temperature and a lot more stable than lithium polymer batteries. And another important thing to note here is both the charge controller and the battery have Bluetooth connectivity, so we can log into both of those, change certain settings, and also monitor the health of the system as it's running. It's a very helpful feature for us, as we didn't have to break up the multimeter every time we wanted to see what the system was doing.
So looking at the budget for our project, we had an approximate prototyping budget of $1,000 that was set by our sponsor, Consultant Designs. And there were two notable budgets that we can look at here, one for the spring 2025 and one for the fall of 2025. For spring 2025, the budget consisted of our solar panel, our charge controller, our battery, and then the necessary fusing and cabling required to wire our sign and make it functional. And this rounded out at $639. Fast forward to this semester, we discovered some dimming capabilities that would give us a lot of added benefit to our system. So this entailed adding an LED driver, a bus bar, and a VE direct cable to our system, which rounded out the fall budget at $681. So the testing for our system entailed three different kinds of tests: charging tests, discharging tests, and DIN testing. We wanted to do this testing for two main reasons. One, to validate our components specifications and make sure all of our components were performing at their what they were rated at in the specification sheets. And we also needed to validate our Excel models and make sure what we were calculating theoretically is what we were getting experimentally. So the first image here is a picture of our charge test. So this entailed connecting our solar panel, our battery, and our MPPT charge controller, and letting the system run outside for a designated amount of time, monitoring the system and recording the data. Then we could later compare our theoretical results to our experimental data. And the image below is a discharge test, which very similarly we set up and monitored for a designated amount of time. This entailed connecting our battery, our MPPT charge controller, and our LED modules. And the images on the far right are captures of our Bluetooth apps from both our Lifetime battery app and our Directional MPPT charge controller. The first image is the Lifetime battery app, and this gave us a lot of real-time data so we can monitor our system and have a really good idea of how it was performing real time. So we could collect data points such as power, current, voltage, capacity, and two additional very important data points that we had access to that gave us a really good indication of how our system was performing was the state of charge, the SOC, and the estimated hours to full charge. Again, these gave us a really good indication of how our system was performing and how long it would last or not last. And the image, go back real quick, on the far right is a screenshot of our Victron app. This gave us a really good indication of the entire system. It gave us similar information, but also for the solar panel, the battery, and even the LED modules. So here's a screen capture of our charge testing data, which was done on September 11th in partially cloudy conditions. It started at 9:40 a.m. and went for an hour and 20 minutes until 11:01 a.m. We took data points: voltage, current, capacity, power, state of charge, and hours to full charge. And really what we were looking at, the best numbers to give us the best indication of how our system was performing, again, was that state of charge and hours to full charge. So if we look at the data at 9:40 a.m., our state of charge was 56%. And by 11:01 a.m., we were able to increase that to 67% capacity. And looking at the hours to full charge, again, at 9:40 a.m., we were at 4 hours. And by 11:01 a.m., we were able to drop this down to 2.8 hours. And going to restate it one more time that those are the best indications of how our system performs and gives our best idea of real time of how it's going to behave.
Now, as for, well, lighting the LEDs, if today on grid power, they run at full brightness anyway. Not all customers need the sign to run at full brightness throughout the entire night, and it can actually add a lot of cost to our system. If we look back at the case we just had earlier, where Brookings all night long needs 225 watt panel and a 60 amp hour battery. You can't just buy a 60 amp hour battery. We can buy 50 or we can buy 100, and 100 is huge, really hard to package into such a small sign. The other thing too is the size panel you would need would exceed the 2 foot by 4 foot requirement. So in this case, by just adding $40 to the cost of the system with the parts to allow us to be able to be dimmable, we can save actually $260 by not buying such huge oversized components. And all it takes here is a buck driver, which we were able to get for about $20, and then we had $20 in the other wiring. And this takes a 5-volt, 160 hertz PWM signal out of current controller, and it basically all it does is it turns on and off the LED really fast, faster than the human eye can see, and it averages out to just seeing higher or lower brightness depending on what we set the duty cycle for. And here is the program actually inside the charge controller itself that controls both when the LEDs turn on and off, and how long they run for, and at what brightness. So on the left side here, these are the parameters that basically let the charge controller decide based on panel voltage when it's daytime or when it's nighttime. There's also delay in there to make sure that we're well above or below those thresholds before any action is taken. That way you don't get the sign turning off and doing weird things like that. Then on the right is the controls for setting how long lights are on. So in this scenario here, I have lights turning on at sunset and staying on for 4 hours at full brightness. At that point, they will shut off. And then the charge controller can learn over the course of a number of days roughly when midnight is. They can learn the overnight cycle. And from that, you can actually have it be predictive, and it will turn on our load an hour before sunrise in this case. And this is a good case where you might have a fast food restaurant that stays open maybe until midnight, and then it will open again maybe around 5 or 6 a.m. for breakfast. Here we did some testing out in the wild with the dimmable LEDs being controlled, and we found this quality inside here in Brookings compared to, on the left is the sign at 100% brightness, on the right is at 30% brightness. And we found that 30% brightness to our eyes, which is not as good as measuring it with like a candle meter, but is what we have access to, we found it was about equal brightness at only 30% power, which is really nice to see that you don't actually need to run the sign full bore in order to make it equivalent to what's out there today. Means there's lots of room for the customer to choose what they want in terms of brightness and runtime and get the most out of the system, and also not overpay for components.
Results are dimming testing, we have established that 30% brightness as a minimum band. We're able to go back to the control system and do some optimization once the designs. So we came up with a new system design as a result. This one assumes it can run 4 months with a 200-watt panel and 50 amp hour battery. So standard component sizes. The system will be applicable to install it in a wide variety of locations. That's dimming. For example, in Brookings, we could power the system for maximum 11 hours at full brightness at night. Past that particular time period, we will reduce them 30% or up to a maximum of 4 hours, depending on the length of the night. In comparison, if we were to install the system in Houston, Texas, we would be able to run full brightness every single night.
So to wrap up the presentation with the main conclusions that we want to draw from our project, first we're going to revisit the significance. We really want it to be clear that the significance of our project is that our solar power system pays for itself on day one. The cost of our components to make our system is cheaper than the cost of the permitting and the trenching to run the conduit from the building to the sign. On top of this, there are also additional savings, energy savings, because solar power is free. So for every day and every year that our system lasts, you will be saving those energy costs. Moving on to the final constraints, the biggest thing that changed here from the initial constraints are the number of LED modules that we are powering. We're no longer trying to power the 80 modules. After rethinking, it is more realistic that we would power 40 modules in a directional sign instead of 80 modules. So that's why that number changed. And then these two are very similar to the initial constraints. The sign still needs to be powered every night throughout the entire year. And the maximum solar panel size can be no larger than 2 feet by 4 feet. And the final deliverables for our project, things that we are going to leave with persona signs once we step away and hand it over to them here at the end of the semester. The first thing is our Excel model. This is a very accurate model that can simulate any scenario. As we discussed, you can manipulate battery size, panel size, number of LED modules, hours fully functional, and hours dim. So a very powerful tool that they will have at their fingertips. And we will also leave them with 2 recommended systems, one for the mid to northern latitudes in the United States and one for mid to southern latitudes in the United States. So system 1 will feature a 200 watt panel and a 50 amp hour battery, and system 2 will feature a 100 watt panel and a 25 amp hour battery. And those 3 things should leave Persona in a very, very good place when we hand it over to them here at the end of the semester.
Snow, how does that go?
So with the tilt of our panel, and there are solar panels here around Brookings. So number 1, it does melt off or slide off right away. If you really needed to, somebody could go clean it off, but we don't see that being an issue with the tilt. And
So with your guys' 30% dim being almost equal to the eye of the 100% dim, did you guys look at like a distance? Like, can you see it further away, or do you have to be closer to be able to see the sign?
We didn't look at that as much, you know, especially since we were changing these hotels from being whatever they were to, hey, now you're the days in. We're like strictly just trying to get photos before we get kicked out of the location. Like, all right, yeah, that's not good. So, yeah, but if it's equivalent at 5 feet away, it should be equivalent also at 50 feet away.
Okay.
Yeah, and then does the dimming, does that significantly impact the light of the LEDs?
So, those diodes don't care if you turn them on and off millions of times.
When you mentioned your solar modeling, you tested it in September and you gave us an example of time of daylight in August. Was everything designed around like January when it's least amount of sun?
so we did do worst case scenario testing, which would be December 22nd.
For sure.
First day of the year.
In the back.
What are you gonna do in the winter when it drops below freezing and the BMS stops that battery from charging?
That shouldn't happen unless that particular battery gets below 4 degrees. The other thing too is Lifetime does have self-heating batteries, which we would definitely look into for colder climates. So there are solutions for that. That's just the battery we'll have for quick prototyping.
You guys mentioned like cold weather and stuff kind of killed the battery life. Do you have a general lifetime of these batteries and how long they'll last?
We think they should last at least 5 years, if not more, especially since we're limiting that depth of discharge, which should keep the battery healthy.
Have you guys ever thought of like, not insulation, but some protective measure to put around the batteries to extend their lifetime?
In terms of like insulation.
Yeah, it's kind of, yeah.
ET. Problem is with, you know, days and days of cold, it's just not really gonna make a difference because that battery doesn't create any sun. I mean, we're only pulling a couple of amps out of it at most. 80 LED is 2.5 amps. So it's not a lot of current, doesn't make a lot of heat. I don't be concerned if it made a lot of heat, because that wasted energy.
So like today, when it's cloudy, you mentioned that cloudy means 25% of charge. Is that the number? So today, when the solar panel is only generating 25% of its capacity, is that going to charge up, or how would it perform today at 25%?
So I think you guys did a really good test. I wasn't there for that meeting, but based on what capacity our battery had, and we would have to run the LEDs thin probably. And at one point when we dimmed them, I can't remember exactly which thing, I think it was 50%. We still had 21 hours of runtime. So for one day of dimmed, or one day of cloudy conditions, the sun would still be able to run, and yes, we would pick up some solar charge. The problem that you run into is probably 3 or 4 days long of heavy clouds. If that happens, dim the sign a little bit more.
Now, would it automatically dim itself if it knew it was in that predicament, or?
Currently, there's no communication between the car controller and the battery itself. We wouldn't have a way to look and check and see what the battery state is. The other thing too is these solar systems aren't 100% reliable in terms of always staying on no matter what the weather conditions are. I mean, I think everybody's gone down the road and seen those radar speed signs with a little battery warning and they're not working. So it happens from time to time, and that's just gonna be something the customer would have to accept. Is there might be a couple nights a year where that sign is dead, but for the situation where you have to pay $8,000 to get power to your sign, that might be worth not paying that money and instead saving it on this.
Could you, in theory, just take the battery out and like charge it indoors using grid power and then just bring it back outside in that situation?
Yes, depending on where your battery is housed inside the sign, or if you have a separate enclosure, I don't know how often you want to take a battery out of the sign and put it back in, but yes, that would definitely be an option.
Cleaning your solar panels, how often do you have to do that? Have you looked into that at all?
We looked into testing how the panels perform when it got dusty or if a leaf fell on it. Certainly, if a leaf falls on it, it needs to be cleaned off right away. From our research and from our actual testing, having one of those cells covered on the panel significantly drops the performance of the panel. We contacted some manufacturers and they're like, "Oh yeah, that's totally normal for your panel to just tank if it gets a leaf on it." We're like, "Great, that's fun." So that'll have to be at customer discretion. Probably ideally clean the panel once a week, but it entirely depends on how dusty it is.